खाना वगैरह नहीं किया हुआ मैंने किया क्यूबरनेटीज डॉकर काम किया मेरा प्रोजेक्ट मेरा काफका पे नाम मैं 7 साल पहले गया 2017 का प्रोजेक्ट
काफी खराब एक्सपीरियंस था। हाँ वो मिला ही नहीं तो
कभी टीसीएस में था किस्मत थी कि ज़्यादा काम में नहीं मैं टीसीएस में उस वास्ते जो भी टीसीएस में कल मैं
हाँ ना स्वास्थ्य उस दिन आया तो पार्टी
अच्छा हाँ टीसीएस में था उसको कुछ काम नहीं मिला वहाँ पर बहुत लोगों को काम नहीं मिलता मेरे साथ में लोग थे जो भाई 1 साल से बैठे थे वहाँ पर उन्हें कोई काम नहीं मिल रहा था उसके बाद भी उनको मेरे जाने के 2 महीने बाद काम मिला उनको इसका टेस्ट
नहीं आता तो अगर काम नहीं मिलता
को जावा वगैरह का पहले प्रोफेसर बनना था लकीली मेरे पास जावा स्पार्क का प्रोजेक्ट था
Yes, come on. Well, I'm using this. I don't know this. I don't know.
Like recruit people before they come. Right you. That's all. Right. How are you doing?
हाँ मैं देखा था
For the first one, I just run the tests locally. Is that enough? For the first one? Yeah, I mean, I passed the test on it. It's
Hello. Can everyone hear me? Can you guys hear me? All right. Okay, so welcome to Lab 2 for Intro to Deep Learning. I think, are we echoing on Zoom? Hello? Okay, it's good. Yeah, so today's lab is going to focus on debugging deep learning networks. And just to see, has everyone started on their P1s? Yep. If you don't know, then the early submission is due today. So the purpose of this lab is basically to expose you to all of the errors that you're going to come across while debugging your part 1s and part 2s, And we'll try to give you these toy examples that you have to work through so you understand that you know how you should debug these errors. Now, the workflow for today is going to be that you should go over to the Piazza post 163 and download this notebook and the data and just upload it to a free T4 instance. And we'll give you 12 checkpoints that you have to go through, and me and Kate will walk you through those checkpoints, and then you have to submit a Piazza poll for the ones that you were able to complete. So can you guys, has everyone already got the notebook? Yeah. For everyone on Zoom, can you react with a thumbs up if you are looking at the notebook and you've uploaded the notebook?
Do we need additional computation for this lab, or is it?
No, a normal CPU or T4 is fine.
Don't know when you can re-ask. Re-ask.
Has everyone got the notebook? And on Zoom, we don't see many thumbs ups. So please thumbs up if you have the notebook, or write in the chat, or just let us know before we start. Okay, I'm gonna start now. Okay, so debugging deep learning networks. So as we can see in this image here, we know that neural networks are essentially a black box, and there's a lot of stuff that goes into developing these models, that goes into implementation, data set construction, model fitting, hyperparameter choice. Essentially, there are many points where your code can fail, and it's hard to know where exactly it's failed. So that's what we're going to address in the lab today. I'll be taking over part one. Now, as I'm sure many of you know, part one, we're basically working on building a clone of PyTorch, which we call MyTorch. And this is the general structure of the handout that we give you. Now we have a folder called MyTorch, which has two subfolders. One is NN and Optim. NN has your layers like linear and convolutional layers, and your activations and losses. And Optim basically contains the optimizers, such as ADAM, RMS, prop, SGE. Now, both of those elements come together in the models folder, where you make your CNNs, RNNs, and for homework 1P1, you made your MLPs with different layers. Now, firstly, a common error that we see students first encounter is that they see the error called no module name MyTorch. This is basically when you are executing the autograder when you're not in the top level directory, or you're in an incorrect virtual environment. So make sure to execute the autograder only from the top level directory. Now, what is the autograder? The autograder is basically a mechanism we built for you to test your own code. And there's a file called autograder_flags where you should declare the test that you want to run by setting true for the ones you want to run. Now, the autograder basically tests you on two things. One of them is closeness, and one of them is architecture. So closeness is essentially checking how close the values that your network generates, how close are they to the correct or the reference solution. So the first checkpoint that we have for you is really easy. If you run the first cell, you can see that the closeness test fails. That's because our numbers are not close enough to the tolerance level that we have set. So let's just change them back to 2 and 4, and we can see that the closeness test should pass. Yep. Is everyone following with that? Okay, now we have the architecture test. The purpose of the architecture test is just to see that the network that you've developed, does it have the correct architecture from what we expect? Let's say that you were asked to make a weight matrix of the size 3 by 2, but you incorrectly made one of 3 by 3. We're going to test you on the shape, and you see that the architectural test fails. But again, if we correct it, we see that I don't know why the test fails. Okay, that shouldn't happen. But let's now see. So basically, the architecture test and the closeness test, they come together to test you on all of the parts of a neural network, right? So how are we going to teach you that? We're going to teach you that using the linear layer example from homework 1P1. And what we have for you here is a buggy version of the linear layer. And we're going to work through these bugs using the tests to show you how we should debug. So firstly, here is the linear layer from homework 1P1, and we also have a ReLU from homework 1P1. So let's run these two cells and run the test. We now see that the tests fail. So firstly, the forward pass test has failed. And whenever you see a failing forward pass, you should start at the beginning of the chain. And the way we've implemented is we have a linear and then a ReLU. So first, let's go to the forward method of the linear class. Okay, so can anybody look at this forward method, especially the forward equation, and tell me what is the error in the forward method? For reference, you can look at the equation here in your notebook. Sure.
Is it self dot A times self dot W dot T? Should that be matrix multiplication?
Yeah, exactly. So for everyone on Zoom, we've incorrectly implemented element-wise multiplication here, but we should be implementing a dot product. So let's go ahead and fix that. So now that we fixed that, we see that the forward pass of the linear is now correct, but the ReLU still passes. So following the psychology of debugging everything in parts, now let's go over to the ReLU forward pass. Can someone now tell me what the error is in the ReLU forward pass? It's really easy. Exactly, it should be a max. So now we can test, and we see that the forward pass is fully correct. Is everybody also following with that? Okay. So now that our forward pass is correct, let's test the backward passes. So we see the backward passes are still failing. And whenever you see an incorrect backward pass, you should move in the opposite direction to the forward pass, because as we know that the gradients flow backward in a backward pass. So you should start at the end. In our case, we start at the ReLU. Right. So similarly, can someone tell me what the errors is in the backward pass of the ReLU? You're close, but try to think about the forward equation. Which derivatives do we want to propagate backwards? Is anyone on Zoom? Yeah, I guess we could do that. So what you're saying, we could implement it like that. Yeah, you're right. But okay, we could do that. We could also just say wherever a is greater than 0, we could give 1. It's the same thing. Everyone following with that? For people who just walked in, you can download this notebook on Piazza. It's post 163 and follow along with us. Yeah, so we fixed the ReLU backward pass. Now let's go ahead and test it. So we see the backward pass is still failing even though we fixed it. So this is going to be something that you're going to see a lot in your homework part 1. So can someone tell me, even though we corrected the backward pass, why is it still failing? This is something that is like, it's a very basic mistake that we would not consider. Yeah, sir.
Did you run the cell,
Yeah, I ran this for the backward pass.
or did you run the cell for the
For the LE backward?
for ReLU? Yeah.
Yeah, sure. I did. Okay, so basically you need to rerun the forward pass because the gradients are stored in the forward pass that are reused in the backward pass. And more importantly, you need to make an instance of the neural network once again. So if we run the forward pass, we see that the ReLU backward pass now is okay. So now we move backwards. After the ReLU, we have to debug the linear backward pass. Now this one is pretty easy. Can someone tell me what the error in the linear backward pass is? Yep.
Should be matrix multiplication.
Absolutely. Right. So we corrected the backward pass. Let's rerun the forward pass and make an instance of the class again. And our backward pass and forward pass is now correct. So that's literally it for how you should debug P1s. Always make sure to look at the errors. And now I'll just tell you about some general tips that I would want if I was starting the P1s again. Firstly, always work through the shapes manually. What I used to do is I would put comments to the side of code like this and put the shape maybe 3, something like that, to keep a mental note of what shapes are going in and what shapes are going out. And alternatively, if you don't want to do that, you can just put a bunch of print statements to see where the shapes are messing up. And that way you can work backwards and figure out where your errors are really starting. And the third point is very important, to invest time in reading the write-up. I know the write-ups are huge. They're like 50 pages or something. But spending an extra 20 minutes to read these write-ups can save you hours and hours of debugging. It's not a lot in homework 1, but as you get into homework 3, it's going to get even heavier than what it is now. And finally, if you guys are used to using traditional debuggers like the ones you see on VS Code, you should go over to the course website where we prepared a recitation 0, where you can use, like we'll walk you through how to use a debugger effectively. Now to help you debug the part 2, I'll hand it over to Kate.
Thank you, Vishan. Now we move on to part 2. Coming back, for everyone who just joined, please go to Piazza Post 163. We have a notebook and data, small data set that you will need to successfully run this lab for part 2. To begin with, so we have the ideal workflow for part 2. You download the notebook that we provide you. You then complete all the to-dos, and then as you want to move on from basic cutoff to a high cutoff solution to get the best score, ideally you would need to experiment with your study groups. We will be assigning study groups, I think, this week, and we will be releasing them, and so then you'll be working in your study groups. To remind you, so part 2 components, we basically have 4 of them. We have data loading, preprocessing, moving on to building a model, then training and monitoring, and then finally testing and Kaggle submission. During each of this part, there are different issues and errors that might be happening. And I think, how many of you have started homework 1 part 2 already? Yeah, so pretty a lot of people, so you might already see some of those errors. So today we'll try to cover them to make sure they don't happen again. To begin with, please run this cell installs, which will basically install main things that we will need for today's lab. It also includes a cell to mount your Google Drive. Ideal way, we don't need additional compute for this lab. So what you can do is just go to Piazza Post, download data and notebook, and put in your Google Drive folder, and just run from there, and it should work. We don't have any major compute thing here. have anyone run it? Or just let's wait for 1 minute. Yeah. Yeah. If you ran it already, just put maybe pluses in the chat in the Zoom, and then just maybe in 1 2 minutes show of hand here in class. So again, the workflow here, you just upload these materials and run this cell. This will help us to get us started with the rest of the tasks in this notebook. Have you guys, can you just show the hand, like who did it already? Okay, some people, okay, good. For everyone who joins, we're working with a notebook at Piazza 163. So just upload it and we're moving on with part 2. So before we begin, just very first initial tip, we recommend not hard-coding all the values that you use in your notebooks. So in the option A, you see that the student hard-coded basically everything they use. But in option B, we highly recommend using configs files. There are 2 ways to go about it. So you can approach one, you can have a config dictionary, where you store all of your files, all of your hyperparameters that you will be using across the models. And approach 2, you can use a YAML file. So any of these approaches is fine, as long as you're keeping everything in one place, because usually what we see in office hours is that students initialize some of the values on the way, and we just don't know like where it's coming from, so it's nice to have everything in one place. It's easier for debugging, and I think it's easier to finish the homework faster. So then just run this cell. This would initialize your config files and just print, there's an option like example how you would call, for example, batch size that you would use. So this should print, and you should see 10, because we initialized batch size of 10 here. So just run this cell. Okay, hopefully everyone were able to first of all upload this notebook, run the installs and run this cell. Moving on, before how we get started with every homework or any deep learning assignment. First of all, we try to understand the task. What is our axis and why? So what are we building and what is our problem? So how we usually go about this homework, imagine we gave you lots of different data. How you would go about it, you would just imagine like 2 files, just literally, and just plot them and see what's in there. So here, in this line, please provide a link to your data where you uploaded the data from Piazza, 4 files. It's 2 MFCC files and 2 transcript files. And please provide a link to those files in here. So once you print it, you would see that actually your directory has these 4 files. Okay, have anyone done it? Yeah? Okay. Some people, okay, great. So now, since we already provided a link to our files, first thing, like very basic, we just we take just one file and plot it to see what's in it. So here on this chart, we basically plot, this plot would be just our MFCC file, and below would be a corresponding transcript. So what is our task in this homework is trying to transcribe someone's voice. And so our axis would be here, our file, our actually voice, how it goes, and then transcript is basically phonemes. Phonemes is just like small like sounds, transcribed sounds. before we move on, if you just look at it, how do you think it's easy for the model to work with this type of information? If we just look at it, do you think there's something that the model might be struggling with if we just provide the files as it is? Yeah, so any ideas? If we just give like all array of all time step at just a single transcript files and just ask it to match it, would it be able to do this effectively, or what do you think might be happening? Yeah, any ideas? If we just look at it, imagine, yeah.
Well, the scale of the values seems to be like really different. Like there's a huge gap between frequencies over 25 and above.
Yes. Yes, that's one of the issues, that values are not normalized, and you can clearly see that the model might be struggling. Also, if we just ask the model directly to predict everything like exact correspondence, we're basically asking to predict, take one voice and transcribe it like at one go, it might not do really well. So what we're trying to do is break it into smaller pieces and try predict one by one. So the example would be, instead of using a whole materials and whole data, we can break it into smaller pieces, and those pieces are called frames for MFCCs and phonemes for transcripts. So we just create smaller pieces. For example, for letter W versus for letter K, we create a what is corresponding thing, and then our modeling problem would be to match and learn what does K look like, what does B look like, and this apparently an easier approach. So how we go about it? Let's look at very toy example, and there is code about it as well. So imagine we have just two audio files, two MFCC files. So the dimensions of this would be, and imagine each audio has just 10 time steps, super easy, and 27 features. First step we do, we just normalize the data, and this doesn't change the dimensions at all. All of those steps you would be following your dataset class, and if you follow them, your dataset class would be very successful and pass all the tests. So we load our MFCCs, we normalize them, it doesn't change the shapes or whatever. Then we concatenate them all together. So at this point, shapes obviously change because we add one file plus another. Fourth one, then we pad our data with context, because if we want to have successful frames, we would do that. Our context would be of different sizes. Why do we use context? For example, when we are predicting letter W, maybe it's useful for the model to also have access to the previous data. That's why we use the context. So sometimes for the models, it's easier to know what was before, and maybe sometimes what was after. So that's why we add some arbitrary context. And then finally, we break our data into frames. So we decide with our frames, so just break our whole data set into smaller frames that will be used for modeling. Optionally, if we want, we use time or frequency masking, which means we mask certain components within this data set. And then most important thing is we flatten convert to a tensor, because this is what our model would expect if we are working with PyTorch. And finally, we just don't want to train the model on one by one. We group them into batches. So one model run would be operating on the batch size instead of one model. And so here we have all of this code for this. Here we have two types of data we use, toy and real. Toy would be just to understand what are the shapes. Real, would be for using and plotting the data. So here what we do is very simple, and basically you would be following a very similar logic in your dataset class, which you're using for homework 1P2. Here just a very simplified version. So we have a toy, we initialize the dataset. If we want, we normalize it. Sometimes we call, in the notebook we use semestral normalization, but essentially just regular normalization. The most important thing, a common mistake that students do, they don't initialize the correct axis, and then the data is normalized across the different cron axes, and the model doesn't perform well. So next, we concatenate them all together, as we mentioned. We pad them, we extract the frames, and we group them into batches. And so if we run this, we would see that individual frame we had, the very first one is just 10 time steps by 27 features. If we concatenate them, it's doubled because it's 2 files. If we pad them, here I think the padding is 0, context is 0, so we don't see any padding, any padding, but if we add like context 5, it would change because we add 5, which is from 2 sides, would be 30 in total. Then we calculate the number of possible frames. We see it's 20 in this example. We calculate the shape. We specify number of batches, and that's how like our single batch would look like that we will send to our model to train. So the very first question here for this setup is, when you look at those dimensions, what do you think is different from this one compared to your real homework 1 part 2? When you looked, I think those who did like especially homework 1 quiz asking about dimensions, what do you think is different, particularly about MFCCs? As a hint, like how many features did we have in our MFCCs in homework 1 P2?
28.
28, yes, exactly. So the only difference between this example and the example in homework 1 P2 is the number of features. So here we use 27. In homework 1 P2, we have 28. So that's the only difference, just the input size. The rest of the example is pretty much the same. So all it does, this function, which is basically very similar to what you do in dataset class, takes all of the information in Fibro configs, takes a raw MFCC files, and sends it batches of frames to the model. This is for MFCCs. So remember, we wanted to break it into smaller pieces. We did this for MFCCs. Now we do exactly the same for transcripts. This would be easier. All we have to do is we load a transcript, we remove start of the sentence and end of the sentence characters, we concatenate them all together, then we convert them into a numerical format, because originally it was like letters, which is, yeah. And then finally, once we broke them into smaller phonemes, we can group them back into some batches, which using the same batch size that we use for MFCCs. So here is the example, pretty much similar. So we take the data. Here's how it looks like if we just use in toy. This is a list of all the transcripts. This is ideally what your model should predict and match with those voice above. We remove end and start characters. We combine them together. Then we have this map, and we'll be able to map each individual phoneme to a number, which are converted to a number, and then we're able to break it into smaller phonemes and batch it. So if we run it, we would see that originally this was our transcript. We have 13 characters. We removed SOS and AOS, so obviously from this example, we don't have them here. The length reduced by 2 because we removed them. Then we concatenated 2 transcripts together, so it's 11 plus 21. Yeah, 21. Then we have phoneme to index mapping. So basically, see, like for example, silent would be 0, AA would be 1. We combine them together and convert it to numbers. Now we have this. And so in the end, this would be sent into the model, these numbers instead of this. And if we want, we break it into batches, and would be, for example, if a batch size of 5, so for example, this would be batch size, first batch, 5 numbers would go in, then second batch, and we will have like almost 4 batches here. So the very first question, not the very first question, but the question here would be, why do we need here converting from phoneme to indices? Why can't we just send them to the model like this? Why do we need to send the model the numbers? Yeah.
Models can only output numbers.
Yeah, exactly. Exactly. So that's why we need to have this conversion. But when you will be predicting it and submit it to Kaggle, Kaggle expects those things back. So you would need at some point, once you run the inference, like predictions, you would need to remap it back to this. Okay, this is great. Now let's move on. So we talked a little bit about different things we can try. And some of you mentioned about normalization. So if we just run with normalization equals false, let's all run it, we would see that our data looks like this. So can you imagine how difficult it is for them? Like for the model, it's essentially, it's not great to learn that this means silent signal. Like maybe in some cases, yes, but if we just check, it's not usually the best idea. So what we can do, we can change this flag to true, run it again, and we would see this. So we would still see that there's like last dimension, it's not great. And there are ways to go about it, but at least now we have a little bit more diversity across features. And normally it's easier for the model to learn like this. So if you just run it, the second stage, the second thing we tried is, what about context? What about if we want to predict letter, my name is Kate, so like if I predict letter A, my knowledge of A should also have maybe some knowledge of previous letter K. That's why I want to add some context. Imagine I add some context and add like 5. So knowing 5 previous time steps. And here you see that, first of all, we added 5. This is our very first example. Remember, we padded the data with zeros. That's why at the beginning it looks like this. But then in the end, it looks more diverse. If we just change, for example, not take the very first frame, but like 50th frame, we would see that, yeah, this is how it looks like. So for example, this is chair. And we would see that this looks much better with context for the model than just using, context 0. So just compare, let's come back to context 0, it will look like this. But if we add context, let's say 20, it's more diverse features, and apparently it's a little bit easier for the model to associate that with a particular letter. So feel free to play with it. So you can just check with normalization versus without normalization what the size of the context and how it influences actually your data. And this is essential. If you're starting working with a new data set and you want to check like, oh, does my normalization actually works? You can just plot and see how helpful it is. So this is with normalizations, and the questions we are asking here is normalizing the data helpful, and is adding the context overall helpful? And I think we just said that it is helpful. It helps provide more richer features, and apparently for the model, it's easier to learn. So this one was with data preprocessing. So we discussed all of this using just simple functions, but apparently if you're running very big models, it's not really efficient to use just simple functions. We use, first of all, PyTorch dataset classes. So you would put exactly the same logic, but just in a dataset class. And as you see in the homework 1 P2, we had, for the train, we had 2 components, MFCCs and transcripts, and all it does exactly the same. It takes MFCCs, returns a batch of frames, and it takes transcripts and returns a batch of phonemes. The steps, if you just look at your homework 1 P2 class, they look exactly the same. The optional step includes using time and frequency masking, which you can use, or if you have time, if you want to experiment with this as well. So the very first question here, is, what is the difference between, why do we need 2 separate classes, one for train and validation, one for test? Why do we need this, and what is the difference between them?
Because the test data set doesn't have the labels?
Yeah, exactly. We don't have the labels, so our test data set is different. We don't have the labels at all. At the same time, if we are using any transformation or augmentation techniques in a train, for example, time or frequency masking, we don't have to use it in test, because our test is ground truth and we don't have to apply any of those things there. Maybe just a side question about time and frequency masking. I think we covered a little bit of this during recitation 0, but can anyone tell me what the time and frequency masking is? Yeah.
Is when you change a portion of seconds to all zeros or a portion of frequencies to all zeros.
Yeah, great. And why do you think it might be, why do you think we might be using it?
As a sort of regularizer, so that the model doesn't like overfit to certain signals in the data.
Yeah, great. Yeah, great answer. So we're using it exactly. We're masking or putting zeros instead of certain frequencies or time. And apparently, if our model, it helps, yeah, exactly with regularization. And sometimes, imagine if we block certain things in the model and we ask our model to learn the pattern even with those things blocked, meaning we are trying to build even more, a better model, because it can still predict really, really well, even when some pieces are blocked. And then when we go in the real life, imagine like I'm talking and suddenly something interrupted my voice or whatever. This also equates to zeros, certain dimensions of time, and the model will be able to work on this as well. So we're trying just to build a stronger model. Okay, and then also, as you saw, we also specify a batch size. So this means how many frames and phonemes you would send to one single training loop. So here example is batch size of 4. We just send 4 of them and ask the model to run an inference on those, run a train on those, versus batch size of 15. So the question here would be, what do you think is more computationally heavy for the model? And why do we have, yeah, sometimes to balance those two? Yeah.
15, because it's just more ones.
Yeah, exactly. So 15 is more computationally heavy, and sometimes there is a notion that sometimes larger batch sizes, they speed up the training. So sometimes you want to find ideal place between the speed, like basically what actually fits into your RAM. So if you're using Google Colab, you would experiment, oh, I put 512. Oh, and then you check the chart in the upper right corner and you see like, oh, I still have place, so I will increase the batch size. And then at some point you would see, oh, no, I cannot add anymore, so like I just stay with those with this size. So I think, yeah, exactly. It comes at a cost, but it also like it may help speed up the training in some part. Okay, and then finally, I think we answered these questions about data transformations, time and frequency masking. So yeah, go ahead.
What's the issue if we do time and frequency masking in test data sets?
Imagine, because test data set is actually how you go about it in real world. Imagine you deploying your model in real world, and why would you want to block certain things if you want to predict it on it right now, the most accurate possibly? So ideally, like we want to make our model as strong as possible during training, so when no matter what test it is, it still performs well, and we're trying to, yeah, do that. Yeah. Any questions so far about anything? Yeah.
So I was wondering about batch size 4 and 15. If I'm using all my CPU, but not nearly all my RAM, like on the charts, would it be better to increase the batch size, or would increasing the batch size use even more CPU?
I think in current implementation for PyTorch, you will be, if it's PyTorch, you will be needing GPUs to run. You can use CPU, and you can increase the batch size even with CPU, but I don't think the model would run fast on this. You would need to switch to GPUs. Yeah, and if you check the chart, I think you can increase the batch size. Yeah, with that. Yeah. Okay. Any questions for? Okay, so we discussed data transformations, time and frequency masking. One of the things we see with students is try, when you're just implementing them on your own, using some pre-built libraries, try to see how many things you're actually blocking or masking, because sometimes the students come to office hours and they're using like such a very aggressive time and frequency masking, so the model doesn't have any information at all except zeros. So before using any transformation, try plot this and see what's actually happening. Okay, so we're done with dataset class. Hopefully it was helpful. And now we move on to the second part, building a model. So here we have a very simple network. We're also using PyTorch class, which is an efficient way of implementing, initializing a network. We have super simple network. We have just layer 1, layer 2, and the output layer. And essentially what it does, so usually how we read this model, we look at the forward function, and we see like, okay, X. Our X is what? MFCCs. So we take our our frames, and we run them, we call the model, we run them through all of this, and in the end, we receive like some result that would be used for optimization. So what we try to do is take our frames and perform so many different transformations with them that would help us to learn association between the frame and the phoneme. And sometimes the notion will be like, oh, maybe more layers is better, because sometimes our thing is very complicated. Or what if we use like different, how wide is a layer is? So we try to do all these different things and manipulations to make sure our model learns as great as possible. And so here what we do, if we just run it, we would receive this model summary. Apparently, if you done your dataset correctly, there would be no issues with getting this table. If not, you would need to come back and see it. And so here, first question, how many parameters do we have in this model? Yeah. Yes, great. Yeah, this is number of parameters. Usually we have parameter limit for each homework because we don't want to use like, oh my gosh, like trillion billion models. It's a lot of compute. That's why this is how you can check your model. So you can change some of the things, like you can add more layers, you can add how wide the layer is, and this number will change. And so ideally it's, yeah, this is how you can keep track of it. Second question would be, which layer is the most computationally intensive here?
First.
Yeah.
The near one.
Yes, exactly. The very first one, it's the most computationally intensive. And you might see, sometimes it's helpful for larger models when you see like your training doesn't go as planned and you want to debug, and then you would see like, oh, this layer is like super intense and maybe I might think about what I can do about it. And then you see the shape. So the number of parameters decreases. So it's like inverse pyramid. And there is a notion about like, oh, different shapes might be having a different performance. For example, you can think about your problem. Do you want to constantly expand the features, or you want to shrink them, or do you want to keep them all the same? So different things that you might try on your homeworks. Okay, and then typical issue that we start seeing in Piazza is students, for example, this layer. So the previous layer took 200, returned 400. And typically batch norm should be also on the number that received was previously sent. Sometimes students put here, like for example, 200, because they're thinking that maybe it's whatever, it was before, and they get this error that running mean should contain 400 elements, not 200 elements. This means that you passed to batch norm something that was like not correct. So it should be everything there is a flow. If you end with 400, you need to start with 400 here. Very same thing about layers. So imagine, we end with 400 here, and we need to start our linear layer with 400, because if we put 200 here, for example, or any other number, this is a common error that many of you see it's not compatible. So it tries to run this operation, matrix multiplication doesn't work, because the previous one has 400, and the next one is 200. So it's not great. That's why we have to make sure when we do all of this, we have a nice flow of shapes. If everything ends with, yeah, go ahead.
Regarding the shape of the network and the sort of like, basically if we want to keep expanding the features, shrink them down, is there like some like theory behind it, as in like given the data, or like some way to assess the correct way to approach this?
Yeah, overall deep learning is a very experimental field. Most of the networks that you see right now, it was like people did so many experiments in the same setup that we create in this class. When you have study groups, you split the experiments and you check which one works the best. That's actually how it also works out there. And yeah, sometimes you see something works, and then sometimes you try to reason it, but sometimes you can't. Here, for example, maybe there is a way to reason about it. If we're trying to predict, for example, that this is phoneme ch. So maybe what do you think, like if we try to slightly expand it to more and more and more features and then slowly decreasing it back to the output layer, maybe it will be helpful. Or maybe you want to keep it constant. So there are different ways to go about it, and I think like just testing might be helpful. For some of the problems, there are some heuristics, but Yeah, it's lots of experiments.
And we should always use random or maybe some variants.
Oh, you can use whatever. There's so many activation functions. You can test them out. There is GLU, there's ReLU. There are different ways to use them. Yeah. So you can even in this simple model. So linear. For homework 1P2 we just keep linear. As we move on with this course, there will be way more difficult architectures. People, for example, who tried many things of this, they also establish a best practice for certain tasks. So if you look like, for example, ResNet, they have a certain number of layers, what activation they use. But in general here, you can experiment with different things. How wide is a network, how many layers, what kind of activation functions you use. What about the bench norm? Do you want to put it before the ReLU or after the ReLU activation? So there are many things you can try for the sole goal that you want to do this. And the goal is here, we take our axis, which is our original frames, and we convert it back to the output size, which is our phonemes. Yeah.
And again, these just pure experiments.
Yeah.
There's no like, maybe you can look at a graph of how the gradients are working.
Oh, no, that one we go ahead. Yeah, that one is absolutely, yeah. This one is more about like how you set up your experiment. You set as a team, you think like, okay, we want to do this. What different things we can try, and you split them out yourselves. But of course, you analyze your results to make sure like, oh, is it worth pursuing or not? And we will move on and discuss later how we actually go about it. Okay, and so finally, yeah, the thing that we discussed. So how do we read all this? How do we make sense and understand what is a good model training versus a bad model training? So here I'll show 6 different 1DB charts. So instead of we told this is the black box, so like in some sense, we don't know what's maybe like, without looking into this, we don't know what's happening. That's why we try to visualize as many things as possible. What's going in the input, what's go as an input, what's happening during the training, and what is the output. So one way to go about to know what's happening during training, there is 1DB, which is weights and biases program, where you log each of your run. And this would typically log your train accuracy, validation accuracy, and losses during training, and learning rate. Maybe, and you can log anything you want there. And so then when you look at it, you can make sense like, oh, does my model learn? Should I stop it? Should I continue training it, or whatever? So here, let's look at the example number 1. And this would be a bunch of questions. So do we have to stop or continue training this particular model described on the picture number 1? So we see that train accuracy is flat, validation accuracy is flat, validation loss is like, I don't know, went to nan. Like, do we have to, yeah.
I would stop.
Yeah, exactly. There is no way like you have to continue using and training this model if you see charts like this. And there are multiple ways. So what we do about it is typically sometimes the learning rate is too high. There might be issues in the implementation. The optimizer might be chosen like wrongly. There are different ways that you can test and fix in the code when you see this, but you should not be continuing with this model. Okay, model number 2.
You could stop with it. It appears like the training accuracy is stabilized, and because the evaluation accuracy is a lot more volatile than the training accuracy, we'd risk overfitting if we ran for too much longer.
Yeah. What other thoughts? Any ideas? Do we have anything on Zoom? No? Yeah, people on Zoom, what do you think? Like, do we have, just maybe comment in the chat. I see the chat. Do we have to continue or stop training model number 2?
Try changing the learning rate.
Yeah. It's good. Yeah, please elaborate. What do you see?
I mean, as mentioned, we see the training accuracy is increased, but the validation accuracy is really volatile. So it probably means that we might either be trying to like minimize, like we might be like at a local minima somewhere, but you're not reaching the global minimum. So what we could do is probably implement a scheduler or something like that, or like we could use something like simulated annealing, which could help us like explore the space a little and try reaching a global minimum.
Yeah, exactly. Very nice. Yeah, both of your comments are really, really good. And people, yeah, students in the chat, yeah, exactly. Very good comments. Yeah, as we read this, we see that train accuracy is great. Validation is like, well, doesn't converge, great. But at the same time, we look at the learning rate, it's stable. And yeah, exactly. We need to try to implement different schedulers, different versions of it. You can do reduce alarm plateau, but you have to be very, very mindful about parameters you pass. For example, factor and the patience, which means like how many epochs you need to wait before of the bad performance before you reduce your learning rate. So you should say like patience 2, meaning like I'm waiting for 2 epochs, and if the model doesn't improve, I reduce my learning rate by a certain like percentage. And you pass it in reduce alarm plateau. There are also other ways like assign annealing, which just varies different, just tries different variations of learning rate on the way. And there are multiple others, but it's always like you have to implement scheduler. Okay, moving on to the next one, to this one. What do you think? Should we continue or stop running this model?
Maybe continue to see if there's another one.
Mm-hmm. Yeah, that's a good point. Okay, what else do we have? Yeah, go ahead.
Based off the first two, I'd continue, but then the third one, the step is at 0. And so it won't change anymore.
Good, yeah.
Maybe, so this is not really as to whether or not it should continue, but more that if the learning rate graph would be like in log, then we'd be able to see what the step is really at. If it's really at 0, then really like there's no point
Yeah.
in anything else. But if it's like just pretty low, then perhaps, and then we know what the scheduler is, we know perhaps it's just drops quickly in the beginning and then stays stable at like 0.005. And then something like that. Then we can, and then in that case, we'd continue. I think it depends in this case.
Good. Yeah, I really like the comments. Let's also look at the y-axis, like what the accuracy currently, like
30%.
it's around 30%. Like maybe sometimes when we don't know like how good is our model, maybe 30% is great, but for this homework, it shouldn't be like 30. We expect something less, something more. So if you look at this, the accuracy also plateaued at 30%. Learning rate is almost like, I super agree with the comment, is what is the answer for 2? We have to stop training. Question in Zoom. For 3, yeah, so learning rate is almost 0. And so that's why I think it doesn't make sense continuing here because we expect something like, yeah, bigger, larger improvement. At the same time, sometimes when you just run a brand new model and you have no knowledge about like what are the expected accuracies, that's fine. You can like, oh, sorry, maybe okay. But learning rate exactly tells you that maybe you should change something. That's why it's so important to put the right parameters for your scheduler. Because if you put that like super drastic increase, I think this one was like reduce alarm plateau, 80% decrease after no performance. And so in 2, like basically steps, it was gone. So it should be very, very careful about selecting the right parameters for your scheduler. Okay, and so the answer for number 3 was to stop. And then number 4, what do you think about this one? So there's the question in chat, what is the industry standard for train and val accuracy? It depends on the problem. Sometimes, in this case, we're working on, maybe it's a well-known problem, but when we try to transcribe what the person is said, like actually phonemes, and the accuracy might be higher there. So like 70, 80%, maybe. And also, since we TAs also tested these homeworks and we know we have a sense of what are their accuracies, we might have like, 70, 80% maybe. We don't know, it's different. But at the same time, I think if we just do something brand new problem, for example, I don't know, just trying to decode, I don't know, brain, what the person is saying by looking at their brain chart. It's extremely, extremely difficult problem. You will not be able to achieve it like with, gosh, 70, 80% is like a miracle. That's why there would be a smaller one. So it very much depends on the problem you're trying to solve. Yeah. Yeah.
So I was thinking in this case, if I was thinking like it would be better to probably stop the training, and my reasoning for that is because as you can see, like the train accuracy has increased, val accuracy has increased, and it's sort of stabilized. It does seem like even though there's a gap, there might be a bit of an overfit, but the val loss has decreased significantly. But if you see the learning rate is really small, and it's kept on decreasing till it's like we eventually stopped. So I think like we should stop, because like if we'd go for just smaller learning rates, then there wouldn't be much of a change.
Yeah, good. And students in the chat also reply to stop it. Yeah, exactly. Very, very good reasoning. First of all, we'll look at the accuracy is pretty high, almost. Yeah, go ahead.
What if instead we start from a higher learning rate, so the function do, let's say, more exploration in the beginning, and then perhaps it settles on a lower local minima or just a global minimum, whereas,
Yeah.
that makes sense.
Yeah, that's a good point. Sometimes when you start with a too high of a learning rate, you will see non-values, exactly the same that you saw in here. So this will tell you, oh, this is an upper bound, how I can go with a higher learning rate. But exactly, ideally, yes, you want to start with a high learning rate because, like, yeah, hopefully the model converges faster. But sometimes it's not possible. So yeah, but the idea behind it is correct. Yeah. Okay, so here, yeah, so we see that accuracy is pretty high, and we've been training for already like 50 epochs, and it's pretty good. And yeah, the model almost plateauing here in this example. And I think, let me see, blue one is what? Blue one is train, okay. Blue one is train, yeah, cool. And we see that the model is overfitting a little bit. So when we see the gap between train and val, it means the model overfits, and this is a point when you can introduce different things, such as dropout, or even like time and frequency masking. So this tells you, oh, there is actually a gap that we can build a stronger model for train, and apparently it should increase our validation accuracy as well. Some students asked, what did we do here at epoch 20 that we saw such a great improvement? Well, the thing is, like, if you look at the learning rate, it just reduced dramatically, and apparently at this level, up to epoch 20, it was really hard for the model. I mean, it was fine, but it was like too high of a learning rate. So just by reducing it, we see a big jump in improvement. At the same time, it's very important to say, like, please save all of your model checkpoints. So there is a way to introduce a code into your train pipeline and saying, like, if this epoch is better than my previous epoch, please save the checkpoints, which includes the model, the state of the optimizer, and hopefully the schedule and learning rate. And once you did this, then you can restart the training. For example, you stopped at epoch 20, and then you have like, oh, what if I want to manually reduce my learning rate? So if you reload the model exactly where it stopped and continue with a new learning rate. So yeah, using that, and you can save your checkpoints, for example, in Google Drive. And it's look like not a zip file, but just like a file where all the information, all the weights of the model and the state of the optimizer, schedule, and learn rate saved. So this is very important thing. Yeah. So number 4. Yes.
I have a question. So you were saying that we can reload a model that for perhaps was performing poorly, and then we use it in a different way. So how do we do that? For example, because the best model would be like .pth. So how do we do that in code, or we just supposed to?
Yeah.
Like, I don't know how.
Yeah. You exactly. PTH would be the extension in which the model is saved. All the weights are saved. You can just you can just Google it and see in a way like how you can save the checkpoints on the drive. So you just like take the model and save it. We can post, I think, even on Piazza if you don't find the ways to do it. Yeah.
My question is not on saving. I know how to save checkpoints. I'm saying calling the model that has been saved. For example, the one that you stopped and then now you want to start, like how do you call that in the like the code base that we've been given? That's my issue.
Yeah, the way how it goes, if you see, what is this? Okay. If you see this model, so when we go in the training, oh, I think someone is already sent, yeah, Vishan, thank you. How it goes about it. So when you initialize your network, you initialize your network, and then you say, there's a command in model dot, I think, update or model dot upload. I don't remember. Which basically tells you to upload the last checkpoint and use it. So there is a way when you will be calling like a model. I don't have this code right here, but like here, for example, you initialize your model, you say a model network, which means like it's from scratch, but then here would be model dot, and you will upload the checkpoint you cut from the drive, for example. Oh, and exactly, I think Ahmed is commenting that we have exact code for saving and loading checkpoints in recitation 0. Yeah. But the answer would be like you initialize the model from scratch, and then you would upload the weights you cut from in the PTH file from drive. Yeah. Okay. And follow-up question was about, so we were talking about different performances. There is no industry standard. And the question in chat was, oh, what are working in projects, for example? How do we know? And usually, so people who are working on projects, you will be defining your own problem. And usually we will be starting with a baseline implementation. So imagine you're working on exactly the same problem, and first step, you would go and find the most relevant paper that was there on that topic, see what the results they got, say they got like 80% of accuracy. And the very first step you do, you would take the code and the implementation, try to rerun it, and see can you get exactly the same accuracy. And that way you establish some baseline. And once you have those baseline, you will be working on different experiments and tests to improve that result. So when you don't have an industry, you need to create your baseline, at least for yourself, either by checking some relevant papers who worked with a similar data set, a similar problem, or by just, if it's a brand new field, like extremely new everything, you just run a bunch of experiments and try to establish baseline yourself. But it's very unlikely that no one have done it before, at least a comparable field. Or if, for example, you can say, if we're working, maybe no one have done it exactly the same, but maybe they did it in a similar field, maybe with different equipment, but for the same task, you can use it as a baseline as well. So importance of a baseline is huge, and there are ways to establish it. Okay, moving on, we have final 2 charts. So number 5, so here solid lines is train, dotted lines is validation. Here we only plot training loss and validation loss. We don't plot accuracies. So what do we think about this one? Okay.
I mean, stop a long time ago because it's overfitting.
Yeah, exactly. It overfits. And the nice thing about the scheduler, so I think it's a reduced alarm plateau is really nice. Yeah, reasonable decrease, but yeah, exactly. It overfits and yeah, makes sense. Good point. So the answer would be here to stop. But here you see, like we didn't plot the validation accuracy, so maybe it's still improving. So we need to check also, sometimes validation and train loss like plateaus, but still like we might see a little bit improvement in validation accuracy, so that depends. But yeah, exactly, this one. Okay, and then the final one, number 6, same. Solid lines is train, dotted one of validation. Yeah.
I could keep going for like a little bit longer. It's not gonna get rid of more out of it.
Yeah, yeah.
training accuracy already at 100?
It's a training accuracy, where?
I'm trying to see in the, I guess I can.
Oh, sorry, it's a solid lines is train, dotted lines of validation.
Yeah, it looks like the training accuracy is at 100 already, so I don't know, like.
Oh, it was something like close to 90, I think. Yeah, here.
I see.
It's, sorry, the scale is like a little bit off, but 100 is, would be a dream, but yeah.
Like,
Yeah, yeah. But I would say that sometimes when we go about those models, if you read some articles, they would say, like, if especially working with other types of models, you would try to overfit as much as possible, meaning like the model perfectly predicts, and then somehow try to introduce regularization on that. So even using that is okay, yeah. But yeah. Okay, people in the, students in the chat, do you think that model number 6, do we have to stop or continue training? Yeah, there's a division. Okay, Jackson, you're saying to stop, or what are your reasoning? What do you think here? Yeah, if you can speak up. Jackson, Austin, or Matya? Please, if you could like unmute your mic and just tell what are you thinking? Okay, so Jackson is saying like it has converged and loss has been stable. Yeah, sometimes, well, in a way, sometimes we care about every single point increase in our validation accuracy, and you will notice like especially in homework 2 part 2. So if you just look at it, you would see that validation accuracy is still increasing slightly. And at the same time, I would maybe try to continue training for a little bit because it's not a flat line. For example, in here for validation, it was a flat line. Train. It was still increasing, let's see. Here, for example, validation orange one was a flat line. In validation accuracy, orange line is flat line, so I would stop it. But here, it's still like slightly increasing. So maybe, yeah, a little bit, just wait a little bit and see what's with it. Any questions here? Okay, so here it would be just provide your checkpoints you have. You don't, if you want, just make some comments. Do we have to keep on stop or continue training it? And that's why it's so important to use 1DB to check those performances. And usually as you work in teams, you will be working in study groups. There's a way to set up a study group, like a joint account. So each of you would see the runs of other people as well, because you'll be submitted to the same thing. And then how it works about, oh, you run these ablations, you check how it works, and then would be like, oh, your model performed great. Okay, let's move on with yours idea, for example. And it's a nice thing to check that as well. So you can, once we have study groups, you can do that, cooperate, and once the team, this important point, once the, for example, team discovered, like experimented with 10 models, and apparently one architecture was the best, each one in the team can use that architecture. You don't have to copy the code from like everything, like the notebook could be different, but the idea what parameters are used, you can share within the team. So that's a great idea. Okay, and then the final part. So we're done with all this, with this dataset class, we're done with that, with the model and hopefully training and finally testing. So the testing one, so in this homework, we're submitting everything to Kaggle. And the key thing, just a tip to check, is make sure that first of all, as we talked about, we need to remap everything from numbers back to actual phonemes. So your submission file should include those like actual phonemes, so it's readable. At the same time, you need to check how many rows in your submission. So if your test data set is actually like 1039, exactly the same number of rows should be in your submission file, because basically you're predicting for each X. So sometimes we see that sometimes students are using, I don't know, they might use confuse the data sets, for example, or use something else, it's important to make sure it's right. Okay, and then I think the question in the Zoom, what happens when the learning rate is constant through training? Well, sometimes you might reach suboptimal results, because sometimes you think like, oh, actually the model would benefit from larger learning rate, and you have no knowledge of knowing because it's constant through the entire training. Sometimes your performance plateaus because if your learning rate is stable, and it's also not great. So I think it's very important to use some automated schedulers, and ideally that are conditioned on the model performance. So if the model is great, just keep it the same. If not, then not. And then great point, I think Ahmed mentioned in the chat as well. So we mentioned there is a way, for example, if you want to run multiple experiments, you would be like, oh, I don't want to test like use the entire train set. I would use 10% of it. Well, I would say like there is a good reasonable approach if you want to test certain like ideas, but sometimes something that you tested on the 10% of the trained data might not generalize to the full data set. So I would say just use a smaller train sets if you want to debug things. But if you're trying to run a real experiment and you want to get the real results, you need to do it on the full one. And the same for the test. Make sure you're not submitting it should be full test set, not just 10% of it, because then the results won't match. Okay, so this is, I will be getting all these questions, but we have this notebook that you can use. This is basically the end of it. And we have a small Piazza post. It's not required, it's not mandatory. Just to reply how many checkpoints you've got through and do you understand everything? It will be very helpful for us, how we structure the follow in the next labs. And if you guys have any questions for your homework, so about chart interpretation, just feel free to ask. Here, I think we have 5 more minutes. Yeah.
The LandDB also tracks the gradient.
What you can do is gradients. Okay. Yes, there are ways this is automated. You can see the gradients. Sometimes there are notions like exploring gradients when they're so big, and when you see that there's a chart and you could see it's like a plot when you can see at which part of a stage your gradients become so big that it's it's not manageable for the model. And there are ways, when you see that, there are ways to use something like gradient clipping. So you would say you introduce a single line in your code saying if my gradients reach 2 of the standard deviation, for example, please clip the gradient by this percent. And that apparently would help the model to come back into the base. Yeah.
Okay.
Yeah. So today is just a reminder. So we have homework 1 P1 and P2 early deadlines is today, end of a day. If you submit them on time plus the homework 1 quiz, you're eligible for bonus points. If not, just move on, continue to the final deadline, which is February 7th. If you go to Canva, Piazza, there are a few things that you need to fill in. So first of all, study group forms. We're collecting forms to form study groups by January 27th. And then within 1-2 days, we'll form the groups and we release them, and you'll be working with your teammates. There is also a form for Kaggle ID submissions. So once you submit, we need to match you with Andrew ID to grade your work. So please submit that form as well. Soon enough, after add and drop deadline, we will be collecting forms for project group formation. So we'll be forming groups of people for the project, and same for homework 5, if you're working on homework 5s. If it's with projects, you will be, basically we will release a list of mentors with whom you can work on your projects. Yeah.
Are we gonna get a confirmation that our Kaggle has been properly linked to the class?
I think just submitting a form is enough. If we see, I don't think you'll get any confirmation, because we have a list of all students, and if we see that someone haven't submitted the form, we'll reach out directly and ask. Yeah, but there are no confirmations in it. Yeah. Yeah, we have hackathon tomorrow from 2 to 5. Yeah, that's primarily all of the things. Thank you, guys. Yeah.
Homework one, part one. If we don't submit, we can still get, let's say, 100% in theory. We just for to get bonus points if you get it all correct.
Yes.
Okay.
Exactly. Yeah, you can still, some of the homeworks would have like, you have to have a mandatory submission. The reason we go about it is because the homeworks are very lengthy. If you just move and start everything before the deadline, there's like guaranteed you won't be able to complete them. That's why it's, if you just make them, yeah, try submit early and start earlier, you have a huge benefit. Yeah, especially model training. Homework 1, P2 is pretty like manageable, like smaller one. But homework 2, homework 3, homework 4, the epoch time would be training longer, there are more data and everything, more complex models, larger search space for ablations. So that's why it's, yeah, very encouraging. Okay, guys, I think it was great. We will post the recording on Piazza. You can rewatch it, and all the materials is already available. We'll have them on the website as well. Hackathon structure tomorrow, the question on Zoom. So the hackathon structure, if the hackathon follows the release of the homework, it will always include the bootcamp. If there is no homework being released on previous Friday, it will be just a regular large office hours and space to cooperate with your teams, finish the homeworks, and yeah, because there will be so many TAs there.
So tomorrow is the second time?
Tomorrow what? Second.
Tomorrow is gonna be like office hours.
Like a regular hackathon, regular one, just a bunch of TAs and students solving their homeworks, like a big office hour, but yeah, yeah, yeah.